So section 1.3, we're just going to finish up today. We skipped a very important idea so that we could get our test in, and that's simplifying rational expressions, especially complex rational expressions. So this one here is not written in complex form, but it is a rational function divided by a rational function. Of course, that division symbol in between there, you're not going to see a whole lot of that in this class because we typically don't write it like that. Because remember, this symbol here also means to what? It also means to divide. So another way that you can write this is the way you'll see it in this class. And you don't have to write this down. I'm going to erase it. But you could write it like this. You could have that quantity and then that whole thing divided by this. Now, back when you were first learning about division of rational functions, you weren't presented with a problem like that because that just looks what? It looks messy. It looks kind of what? Big and formidable and intimidating, right? So you weren't shown that to begin with. But this is how you'll be seeing this type of stuff moving forward. So if you ever see something like this, this is called a complex fraction. And another name for a complex fraction is what? Y'all might have heard it as, it's another comp word, compound fraction. But I don't like to use the word compound fraction. Why? Why do you think I don't like the word compound fraction? What it sounds like, compound fraction? Compound fracture. Ouch. And I had one of those back in middle school. I broke my radius and my ulnar right here on my left arm in a skateboarding accident, and they were sticking out of my skin and blood was squirting everywhere. My parents were out of town, and I had to hold it together for like 3 hours without any pain medicine until they got a hold of my uncle in Marion to give me some pain medicine. So when I say compound fraction, I think compound fracture, and I'm taken back to that time, and it's horrible, horrible memories. So thanks for bringing it up, guys. I don't want to relive that. So guess what I'm going to call it? Complex fraction, because I don't have any aversion to that word, complex fraction. Now, complex fractions are easy to clean up if they're of this form. This is a single fraction, a single term, divided by another single fraction, a single term. And how would you go ahead and eradicate this complex fraction if this is what you started with? You might write it like this up here, or maybe you learned at some lower grade level state change flip, which almost sounds like tricks for a dog, right? State change flip. Stay, the top stays. The division bar changes to what? Multiplication, and then what do you do at the bottom? You flip it. So state change flip works, and it's because dividing by a fraction is the same as multiplying by its what? Reciprocal, okay? So this right here you could write like that, but then you're still going to have to change flip. You're going to have to change the sign and flip this. So that's our goal. Now, once we change this to multiplication and we flip the second fraction, in order to simplify, we're going to want to factor it, right? Because we can divide out common what's? Factors. So let's go ahead and do that. We'll factor the first term, and we'll factor the second one and write it in flipped order. So we can kind of do multiple steps in one. So that's kind of like walking up to the problem. 4y squared minus 9. Does that factor? Any common factors other than 1? No. Is this a special product? Is this like Lysol with bleach? That's a special product. It's a difference of two perfect squares. Yes. And the product of two, the difference of squares factors into the product of two what conjugates? Conjugates. Very good. So this will be 2y and then a 3, and a 2y and a 3. You take the square root of each term. One of them's plus, one of them's minus. It doesn't matter which. Okay, the bottom. We're going to factor that. Is there a common factor other than 1 or negative 1? No. So we're going to have to factor it, and the leading coefficient isn't a 1. What do we say when the leading coefficient isn't a 1 and we have to factor it? Do we go, oh, man, or do we say, yay, hooray? Yay, hooray. Both? Oh, man, yay, hooray. That's weird. Okay. Now, 2 is prime, so I'm not going to split the middle term because the 2 is prime, and there's only one way to factor it. One of them's got to be a 2, and one of them's got to be a 1. Now, 18 has lots of different possibilities, right? You think it's going to be an 18 and 1 combo? I'm trying to get a 9 on the sum. No. So maybe a 9 and a 2, maybe a 6 and a 3, maybe a 6 and a 3. So let's see, if I put a 6 here and a 3 there, let's try it. That's going to give me a 6 here and a 6 there. 6 plus 6 is 0. 6 plus 6 is 12. 6 minus 6 is 0. That's not going to work. So it's not going to be 6, 3. Will it work as a 3, 6? That gives me a 12 and a 3. What's 12 minus 3? 9. Will that work? That looks like it will. Yeah. Now, because I want my sum to be positive, the larger product, which is your 2 times 6, has to be positive, and this has to be negative. See that? So we have a negative 18 for my product. I have a minus 3y on the inside and a plus 12y on the inside or outside. That gives me a positive 9. So guessing and checking is not a bad way to go, especially when one was prime. Now here's where we're going to go change the sign. Dividing by a fraction is the same as multiplying by its reciprocal. And what I'll do then is I'll factor the bottom, but I'll write it in the top. Now there's nothing common, and the leading coefficient is 1. So that's where we say, oh man, this is like riding the kiddie ride at the park. I'll do it, but I don't want anyone to see me doing it because it's too easy, right? It's like for little people. I'm way beyond that. So we got a y and we got a y. And factors of negative 6 that add up to 5, I'm almost embarrassed. Is it the 3, 2 or the 6, 1? This is the one that students kind of mess up on. The 6, 1, you say? So if it's a 6, 1, the larger product has to be positive, and that has to be negative. Does that work? What should you always do when you factor something out? Just to make sure. Just check it, right? You know that your last factor is going to be a negative 1 times 6, which is good. You got a 6y on the outside minus 1y. 6 minus 1 is 5. It works. Okay, good. And then the top one, 2y squared plus y minus 3. Now that's more like the zipper at the Comal County Fair. That one's got a leading coefficient is 2. It's marginally more fun. And what makes it more exciting is you don't know if all the bolts are tightened. That adds a thrill to it. Anyway, you got a 2y and a 1y. Hey, the fair's coming up soon, right, at the end of the month? Yeah, okay. 3 is also prime, isn't it? So it's got to be either a 1, 3 or a 3, 1. So how about a 3 and a 1, since I know I'm trying to get a 1 for my sum? And let's see, it's got to be a positive 1. So let's make that a plus. Let's make that a minus. And you get a minus 3 for the product. You get a 3 minus 2, which is a 1. So there you go. Now that we have it completely factored, even though it's 2 separate terms, what we can really do is we can bring people together. We can reach across the aisle right there and make that a single shelf, because multiplication is associative and commutative, if you want to do that. And now what we can do is from high to low, divide out any factor that is common. Do we have any common factors? 2y negative 3? Okay, let's see. By the way, if you weren't sure how to factor something, anticipating that something might divide out, you can use some of the other factors you've already generated in the top to help you factor the bottom and vice versa. Anything else? Thank you, sir. 2y plus 3? Those are gone. Y plus 6. And? Holy moly. And what are we left with? 0? Oh, we're left with 1, because anything divided by itself is 1. That is amazing. That is pretty. You can stop right there. That's pretty. It's pretty. So you can actually say it equals this. And remember, I said there are several different types of equations out there. We have name equations. We have contradictions. We have conditional equations. If I set that equal to 1, I've created an equation, yes? What type of equation is that? If the left side is always equal to 1 for all values of y, remember what it's called? It's like it's looking into a mirror, right? The left side's like looking into the mirror and sees a 1 and vice versa. What do you say when you look in the mirror? Hey, there I am. That's my reflection. Or that's my identity. The idea, does anyone ever say that? Look in the mirror, hey, there's my identity. This is called an identity. Remember, an equation that is true for all values is called an identity. Like 2 equals 2, that's an identity. So is this. That's weird. What does that mean? That means you can replace 1. Anytime a 1 comes up, like if you're giving someone your phone number and there's a 1 in it, when you get to the 1, you can say what instead? All of that. And it would mean the exact same thing. Right? Now, you may never get any text messages because your friend's going to be like, whatever. I'm going to get a new friend who doesn't like math so much. And then you'd be like, your loss. Your loss. All right, so you got it? Stay, change, flip? Good boy. Let's try this one. I got a single fraction divided by a single fraction. Your main division bar is this one right here. It's a little bit darker, and you notice it's a little bit longer. We are trying to clean up the complex fraction, meaning I don't want a fraction within a fraction. I just want a single fraction, possibly. So what would be your first step? Rewrite it sideways, yeah. Now, we could do better than writing it sideways with the division bar like this. That would be just an extra line. We can already do the flip version, right? Stay, change, flip. Stay, 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 stay. Good boy, good girl. Change. The dog's like, change. You don't like me the way I am? I obey. I stayed. Now you want me to change? That means when you say stay, I should go. No. That's why these aren't dog commands. Stay, change, and then flip. Now when I flip the bottom, I'm going to factor it as well. So the x from the top now goes in the bottom, and x squared plus 2x plus 1, does it factor? It sure does, and hopefully you start recognizing these things. X squared is a perfect square, 1 is a perfect square. So when the first one's a perfect square and the last one's a perfect square, and the middle term is twice the product of their square roots, this is a perfect square trinomial. So it factors into x plus 1 quantity squared. But you can write it side by side and say x plus 1 times x plus 1. Now quickly, how do we check? How do we quickly square a binomial in our heads? Square, multiply, double square. That can be another dog command. That would be one smart dog. You can make a lot of money, right? Square the first, you get x squared. Multiply, you get 1x. Double, you get 2x. Square the last, you get 1 squared is 1. Okay? All right. Now what? Now what? I'm excited. We got rid of the complex fraction, but now that it's completely factored, we can divide out common factors. Do we have any from high to low? We have an x plus 1 down at the bottom and 2 of them up here. So here's what I'll do. You go, and I'm going to put a 1 there. Now, when you divide things out in your work, you can draw a line through it, but I still need to be able to see what's underneath, right? Because I grade your process. So even though it might feel fun to obliterate it, right, and leave 1 left, might feel fun and gratifying, don't do that, okay? What else divides out? Anything? An x, okay? So it's kind of weird when you cross out an x, look what happens. That looks like an x, right? And then we'll exit out. X out the x. It's gone. And what are you left with here? X squared. So you're left with, in total, in the top, an x squared, still times an x plus 1. And what are you left with in the denominator? Nothing but a 1. Right. But anything divided by itself is 1, because 1 is the multiplicative identity.
But you didn't have to show that on the test to be clear? Or?
To put it over 1?
Yeah.
No, you wouldn't need to show that. No, that would be understood. I just want to make sure y'all know there's a 1 in the denominator and not a 0. Some people mistake and they put a 0. Yeah. Oh, good question. Where do we stop? When we're done, right? When are we done, though? This would be a fine answer, or x cubed plus x squared. Either one. They're both equally simplified in my opinion. We just use them for different purposes. So knowing that both of these are correct on a free response, unless it said leave your answer factored or put your answer in expanded form, the bottom line would be expanded, this would be factored. If we were trying to solve, like if this were equal to 0, then of course we prefer the factored version. So they're both good. All right, so that one stay, change, flipped worked because we had a single fraction divided by a single fraction. One term divided by one term, say change flip, it works. C is not a complex fraction. I threw C in there just because I wanted to show you that the crisscross applesauce method works for non-numbers, right? We're wanting to combine these two fractions into one. And in order to add or subtract fractions, we need a what? Common denominator. What is the LCM of x plus 5 and x minus 3? Good. If we had like the numbers 3 and 2, the LCM would be 6, right? The LCM would be 6 because they are co-prime. When you have polynomials, you're going to do the same thing. 3 is a factor, 2 is a factor. They have no factors in common, so their product is the least common multiple. X minus 5 is a prime linear factor. X minus 3 is a prime linear factor. They have no factors in common, so the LCM is their product. So what you could do properly is multiply this one by x plus 5 over x plus 5, right? That would be the correct way to show your work. And the other one by x minus 3 over x minus 3. But the crisscross applesauce method works really great here. Watch this. 1 times the quantity x minus 3. Take the middle sign plus 2 times the quantity x plus 5. All over their product, x plus 5 times x minus 3. And you could probably, with a little practice, even distribute these numbers to these linear factors as you're writing them down. So that ends up being x minus 3 plus 2x plus 10, which could be your first line, all over x plus 5 times x minus 3. And when you combine like terms in the top, then you get 3x, and then 10 minus 3 is plus 7. So that would be the simplified version. And again, in the denominator, whether you decide to keep them factored or expand it, it's kind of up to you. So in order to combine fractions, we need a least or common multiple. The LCM of polynomials, kind of the same with numbers. You need at least one factor of each. And then if there's one that has the higher power of a factor, you take the higher power. So you're sure that both of them go into it. So why do we look at that one? Because it's a nice segue into letter D. The instructions are to simplify. Does that look pretty grotesque? Relatively speaking, it's hard to argue with that, right? Relatively speaking, yeah. Have you seen worse? You have? Where? I was hoping this would be the worst one you've ever seen. Yeah. Yeah. Maybe you've had nightmares where things worse than this have appeared, right? This is a complex fraction. How do we know this is a complex fraction? What's the giveaway? A fraction within a fraction. That's right. You got a fraction within a fraction. So you have a division bar right there, and in the numerator of that fraction, you have fractions, right? Do we have fractions in the denominator? We do. Remember, it's me. Remember that? That little trick? Right? My Halloween costume, a little bit early. It's me. How do we know we have fractions in the denominator? We have what type of exponents? Negative exponents. And negative exponents are fractions in disguise. They're denominators in disguise. So if you ever see something like this, this is mixed notation. I would write everything, because we're going to simplify it, it's easier to write everything in non-negative exponent notation. Okay, if we're combining the exponents, then negative exponents are good. But if we're simplifying fractions, it's a little bit easier to work with out of. So x over y minus y over x. And this will help us review what we're doing. What happens with x? Yeah, let me come off to the side. X to the negative second minus y to the negative second. Is that equal to 1 over x squared minus y squared? Or is it equal to 1 over x squared minus 1 over y squared? And if so, are those the same? They're not the same, are they? Okay, and you can prove they're not the same because remember the second one here on the right, in order to combine them, we need a common denominator. So this right here becomes which one? The one on the left or the one on the right? What do you think? The one on the right is always right, right? Only if it's correct. If it's not correct, then it's the other one. Okay, remember that. That's good life advice. This one is correct. Now, why do I even show you this one? Has anyone ever, you think, tried to do that? Yes. You can fix each term separately. X to the negative second is the same as 1 over x squared. Then you're subtracting y to the negative second, which is 1 over y squared. So that becomes 1 over x squared minus 1 over y squared. Now, do you think state change flip will work right here in this scenario? It could. So if we did state change flip, let's see, that would look like, very good. If you did this, and if you flip that, would it be x squared over 1 minus y squared over 1? You can't do that. That changes that, right? You can only do state change flip if you have, like what we saw over here, a single term divided by a single term. And down here, we have how many terms in the denominator? 2, okay? Now, here's what you might have learned to do back in little school, and it still works, but it takes like 42 hours or something like that. You would get a common denominator in your numerator, which would be the product xy. Then you would get a common denominator in your denominator, which would be x squared y squared. And you would do the work, and then you'd have a single fraction divided by a single fraction. And then after that, then you would do state change flip, right? Why do we want to do all that extra work when there's well, even if you did your crisscross applesauce, that would still be the same thing as getting a common denominator up here and getting a common denominator down there, and then state change flipping. There's a quicker, faster, more efficient way to do it, and who's not interested in that? Don't raise your hand. We like to be efficient, right? Because if we can get done with the math problem sooner and quicker without making the possibility of more mistakes, that just means more time left over for what? More math problems. I'm all for that. So here's what we're going to do. If you ever see a complex fraction like this, and it works every time, it even works up here when you have single terms over single terms, you're going to multiply by a clever form of 1, known as the Lickum over Lickum. So this is called the Lickum over Lickum method. And what does Lickum stand for? Least common multiple. Okay, so you ready for it? What is here's how we do it. You extend this major shelf, the main shelf out. Okay, now you're going to multiply by the LCM of what I call your miniature denominators. All your miniature denominators. I've got an x, a y, an x squared, and a y squared. What is the LCM of all 4 of those factors? That is, what is the smallest thing that all of them go into? X squared, y squared. Good. You need at least one representative of each factor. We have an x factor, we have a y factor, so we know we're going to need at least one x and one y. But then what you do is you look to see which of those has the largest exponent all the way around, and you take the largest exponent, which is in both cases 2. So you got squared, 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 squared. Got that? You take one of each variable, then you come back through and take the largest exponent on each of them. Now, I really did just multiply by what? 1. Now, if you're stuck, is this what you do? It divides out. Yay! One step forward and one step back. Nobody gets too far like that, right? But it could help. That's why there's like a waggle in golf, you know, kind of maybe breaks the inertia. But in this case, we're not going to do that. Here's what we're going to do. Think of this now as an upstairs-downstairs problem. And here's the subfloor dividing the apartment upstairs and downstairs, okay? So forget everything below this line. This is really x squared over y squared. If you want to get your notability, you could really put that over 1 if you wanted to, right? It's really the same thing. And guess what we're going to do with that? We're going to distribute. Again, forget what's happening down below. Now when I distribute, and I pick the right LCM, your denominators should divide out. So when I distribute x squared y squared to x over y, do the division first. That's the whole purpose. What happens with one of your y's? This y will divide out with one of those y's. So I'm going to cover up the 2 and that y. What are we left with? We're left with x times what? X squared, which is what? X cubed times how many y's? Y. So we're left with x cubed y. X cubed y. So people always ask, when am I going to use this stuff? I'm not going to be doing this like in the produce aisle at HEB. Well, you could. You certainly could. But This ability to think abstractly and to organize and to keep track of things, that's training your brain for multitasking and for critical thinking, okay? Now let's do the same thing for the next one. It becomes minus. When I distribute here, what happens with your x and x squareds? One of them divide out, so the bottom's gone, and one of those is gone, and we're left with a y times xy squared, which is what? Xy cubed. Good, xy cubed. Xy cubed. Boom. And we're done with the numerator. We're done upstairs. We got rid of the bunk bed. See that? In one step, we got rid of the complex fraction and combined them. Now we're going to do the same thing in the denominator, okay? We go outside, we go downstairs, knock, knock, come on in. We do the same thing. I'm going to put this in parentheses because I'm going to distribute. Now what happens with your x squareds? They divide out, and we're left with a 1 times what? Y squared, which is y squared. Minus distribute here, your y squareds divide out, and you're left with 1 times x squared, which is x squared. And there you go. Don't that amazing? In one line, we eradicated the complex fraction. Rather than get a common denominator, and then say, change, flip. And then do another line. So we saved really 2 lines of writing just by doing this. Okay, now are we done? No. Because now that we got rid of the complex fraction, now we're back on familiar territory. We can simplify by dividing out like terms. Factors, terms. Terms? Let's see. So this y divides out with one of those, is that right? And this x divides out with one of those, is that right? How am I doing? I kind of felt dirty. I felt a little wrong. Not in a good way. Like wrong in a wrong way. Why do those not divide out? Those are what? This is part of a what in the numerator? Well, it's a factor in this first, starts with T, rhymes with term, right? You cannot divide out common terms, so that does not work. Okay, so let's go ahead and F it, right? Factor. That's what that means in a math class, remember. Even when you're frustrated, just say F it and try factoring it and see if it works. Because a lot of the times it will. All right, so let's go ahead and factor this. The first rule of factoring is what? Pull out your GCF, right? So in the top, anything common in both terms? X and a Y. We got at least one X and one Y. So we'll factor out an XY, parentheses, and what are we left with in the first term? Looks like an X squared and then minus Y squared. All right. And at the bottom, Y squared minus X squared. Hey, you know what? Y squared minus X squared sure looks a whole heck of a lot like X squared minus Y squared. I'm going to go ahead and write that there. Maybe I'll write them directly underneath each other. Put that one in parentheses, and does that work? Are those like factors? No. Yeah, subtraction is not commutative, right? 0 minus 0, is that the same as 0 minus 0? Bad example. 5 minus 4, is that the same as 4 minus 5? No. Remember, in math, it has to be true when to call it a true thing. Always, right? Not just sometimes. Always, always. So what can we do? There's a couple things we could do. I'll take requests from the audience. Any ideas? I see 2 different things we can do. Yeah. You should start recognizing differences of perfect squares. And we have one at the top and one at the bottom, right? So here's a fork in the road, and as Yogi Bear said, when you get to a fork in the road, you need to take it. So we're going to take it. Let's go ahead and factor the top completely then. X squared minus Y squared is X minus Y times X plus Y. And on the bottom, Y squared minus X squared is Y minus X and Y plus X. Okay, now it's completely factored. Prime factored, we should say. And does anything divide out now? X plus Y and Y plus X are now actually the exact same factor. Because what do we know about addition? It's whatative. It is commutative. Subtraction isn't, but addition is. So, Do that. Now, that x minus y and y minus x, man, that still looks super tempting, like up here. Super tempting. Why don't we just divide it out and not tell anybody? Because, I mean, it's so close. Who's going to care? Who's going to know? Are you going to say anything? You will? The world will have something to say about it. Spaceships won't fly. Cars won't drive. Won't work. So are we done? No! Is that what you said? Good. Yes. No? No. Yes? Yes. Yes, you said no. Yes. Good. No, we're not done. Yes. Good. Why? What can we do? Help me. I want to divide them out so very badly. Please. Pretty please. What? I can take out a negative 1. I can take out a negative 1. From where? Where do we have a negative 1 to take out? What? Either or. Good. So let's choose the choose the denominator or numerator. Let's take a boat. All right. Anyone for a numerator? Raise your hand now. Numerator. Denominator it is. Okay. So we'll take it out of the denominator. So we got x times y times x minus y. Now, what do you mean take out a negative 1? Like date it? Hey, negative 1, put on your best dress. I'm taking you out. Factor it out. Factor it out. Yeah. Okay, so in the bottom, if I factor out a negative 1, I'll put it like that. What does that do to both signs on each term on the inside? It changes them. So now I have a negative y plus an x, which I'm going to go ahead and write as x minus y. Are you okay with that? Now, how do we know if that's correct? We mentally redistribute. Negative times positive x is negative x. Negative times negative y is positive y. I like it, I like it, I like it. Now what's happening with your x minus y's? No, they don't cancel. They divide out. I'll forgive you for that because you were the one that came up with the idea for taking out a negative 1. Let me know if you had a good time, by the way. Now, xy divided by negative 1. Can we rewrite that? Yeah, that's negative xy. And there it is. You're done. Sweet. Now, let's come back up here. I said there were 2 different routes we could take. Here's another route. These are difference of squares, so they do factor into the product of 2 whatchagates? Conjugates. But can't we do the same thing up here that we did down here? Can't we factor out a negative from one of those? Yeah. Now I'm going to do it the other way. If you don't want to factor out a negative from the bottom, you can factor a negative factor out from the top. Now if I do that, I'm going to pull the negative out in front already of the xy. So I get negative x times y, and then factoring a negative out of the numerator, I get a y squared minus x squared because it changes both signs. Okay, so even though the negative is in front of the xy, it still came from this third factor by the associative property of multiplication. And the denominator, I'm just going to leave as y squared minus x squared. Now, when you have multiple terms and you're going to divide it out as a factor, please, please, please put it in parentheses. And now what happens with your y squared minus x squared? They divide out, and we're left with negative xy. So a little bit slicker, a little bit cleaner, shorter, easier, but each way works, right? They're both correct. So there you go. Now you know if you have 2 terms and they are commuted with subtraction, they don't divide out, but they can if you leave a residual negative 1 behind. So kind of a little strategy, right? Where'd you get that strategy from? Was that on sale one day at the HEB when you were doing this in the produce aisle? How did you know to factor out a negative 1? Was that given to you by like an ancestor, or have you worked problems like this before, or you're just engrossed in the problem and you know what your possibilities are? That's what it is. Yeah. Same thing with everyone else here. Once you see something as done, you're like, I never would have thought of that. I never would have thought of that. Now that you've seen it done, they're like, oh, now I can think of that next time. Now I know it's possible, right? You can't run no mile in 4 minutes. Oh, yeah, you can. Okay. Now a lot of people are doing it, right? There you go. Now you know what your possibilities are, so you can kind of reference that when you're stuck. One of the things you can do. How much time do we got? 6 minutes? 6 minutes. Okay. Did we finish? We did. Let me give you all one to try, okay? You try. I don't like the word try. I'm going to say do, right? Let's do this one. X negative 2 y squared plus x y to the negative second all over x cubed y to the negative first plus x to the negative first y to the fourth. Want to simplify that. Mean, like average? It is a pretty average problem. You're right. Yes, sir. Oh, you said compound fraction. Say complex. Yeah, complex. That is a complex fraction. How do we know? Yes, you have a fraction, obviously. There's a main division bar, but you also have in the numerator and or the denominator what type of exponents? Negative exponents. Good. So I'm going to give you, let's see, we got 5 minutes left. I'm going to give you 2 minutes to get started on your own, and we'll finish the last 3 together, finishing it. Now, feel free to reference the previous example if you're stuck as to what to do first and what to do second and third and fourth. I'm not sure how many steps this one has. Fifth. Yeah, why? Yeah, it's a splash zone. We got 2 seats in the splash zone. Yeah, I've been talking to some folks that are interested in you doing well, and we all agree you should sit in the splash zone. So just tomorrow when you come, if you want to grab one of those. Right. Yes. Do you have enough for you? Oh, okay. Okay. So sleep in a little later tomorrow. Or show up. Yeah. Okay, let's go over it. The first thing that you're going to do, once you recognize it's a complex fraction, you have a division bar here, and then you got negative, 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 negative. You want to get rid of the negative exponents, okay? So that's y squared over an x squared. Bless you. You could certainly write it as 1 over x squared times y squared, but remember, it's the same as y squared over x squared, which looks a little bit nicer. And then plus x over y squared for the next term. And then you've got in the bottom an x cubed over y plus a y to the fourth over x. So now you could see your layers. You got how many miniature denominators? 4 of them, right? And what you're going to do is multiply by their LCM. The LCM is going to be 1 of each type, so we have an x and a y. And then you take the largest exponent on each type, which appears again to be squared. Maybe I should have invented one that had a cube or something. But if this had been like an x cubed, then we would have to take an x cubed. So 1 of each factor and then the largest of each one. Now I'm going to quickly distribute. I'm going to put parentheses around the numerator and denominator. When I distribute to the top, look what happens. Your x squareds divide out, and you're left with y squared times y squared, which is y to the fourth. Plus, in the next term, your y squareds divide out, and you're left with x times x squared, which is x cubed. And that's the numerator. You're done. Denominator, you multiply, and your y squared divides out with your y, leaving a y, but you still have x cubed times x squared, which is x to the fifth, times y, plus now one of your x's divides out, leaving you still one x, but a y to the fourth times y squared is y to the sixth. That takes care of the complex fraction in a single line. Now, of course, once you get there, I'm going to write the top in alphabetical order, x cubed plus y to the fourth, and we'll factor out an xy, and that leaves us x to the fourth plus y to the fifth. And does anything divide out? I do not think so. Of course, x cubed plus y to the fourth is different than x to the fourth plus y to the fifth, and those do not factor. So we're done. Okay, we're done. That's sometimes you don't get to factor things out, but you try. This goes to here, so this y divides out with one of those y's. So we're, well, it's x cubed times x squared is x to the fifth, and then we're left with one of the y's. Because this is like over 1, remember. All right, so finish your worksheet. You're not going to have to turn it in, but on 1.3, there's lots of problems that have this on there. So I would practice them. You will be tested and quizzed over this material. Tomorrow we start 2.1. Yay! Have a great day.